In this lecture, we will be discussing about the parallel magnetic circuits. A magnetic circuit is said to be parallel when there are two or more parallel paths for the magnetic flux. So, if there are two or more than two paths for the magnetic flux, such a circuit is known as a parallel magnetic circuit. So here in this figure, there is a rectangular frame A, B, C, D, E, F having three limbs is shown. Suppose a coil having n number of turns is wound over the central limb like this. So this coil is having n number of turns, and assume that a current of I amperes is flowing through this coil. So there will be an MMF which is equal to N into I, and we know that MMF is the force that produces flux in a magnetic circuit. So due to this MMF N into I, a flux of 5 Webers will be set up in this central limb. So this flux is equal to 5. So 5 Webers is set up. Now at this point, the flux will have two parallel paths. So at this particular point, flux divides into two, and a part of the flux is carried by this path like this. Okay, and remaining flux will be carried by this path. So at this point, the total flux phi will be having two parallel paths. So the flux carried by the path BCDE is denoted as phi 2, and the flux carried by path BAFE is denoted as phi 1. Okay, so the total flux phi divides into two, that is phi 1 and phi 2, which are carried by the two parallel paths BAFE and BCDE. So we can write the total flux phi is equal to phi 1 plus phi 2. Okay. Now we can draw the equivalent of this circuit like this. So in the central limb there is an MMF. So we can represent that MMF like this. MMF is equivalent to EMF in electrical circuits. So the equivalent electrical circuit is this. So there will be an MMF, then the central limb, it is a magnetic material, so it will be having some reluctance, and let us denote it as S. And the total flux in the central limb is phi, and the flux divides into two, that is phi 1 here and phi 2 here. Okay, so this is the left limb or path BAFE, and this path will also have a reluctance, and that is denoted as S1. So this reluctance denotes the path BCDE, and its reluctance is denoted as S2. So this is the equivalent electric circuit, and we can simplify this again. The circuit can be again simplified. Okay, so we know that in an electric circuit, in a parallel electric circuit, the total current divides and flows through the different parallel branches. So here the total flux phi divides and flows through these two paths. The total flux phi divides and flows through paths BAFE and BCDE. So we know that current divides when there are parallel paths. So we can say that the path BCDE is in parallel with BAFE. So we can simplify this circuit again like, so these two paths are in parallel. So these are in parallel, that means reluctances S1 and S2 will become parallel. So there will be S1 parallel to S2. Okay, and flux flowing through S1 is phi1 and flux flowing through S2 is phi2, and it is the total flux phi that is getting divided into phi1 and phi2, and the total flux is flowing through the reluctance S, that is through the central limb. Okay, and there is an MMF also. Okay, so this is the total reluctance S. So we can simplify this circuit like this. So as the coil is wound over the central limb, the total flux is produced on the central limb. Then flux divides and it is then carried by the two parallel paths. As flux is getting divided here, we will consider these two paths are in parallel, because in parallel electric circuits, current is getting divided when there are elements connected in parallel. So we can consider these two magnetic paths as parallel paths. So their reluctances are represented like two parallel reluctances, and the total reluctance, the reluctance of the central limb where the total flux is produced will be in series with this parallel combination. Okay. Now we can write the expression for total MMF. So here, see, if we refer to this particular circuit, total MMF will be equal to MMF across this reluctance S plus MMF across the parallel reluctances. So we know that in a series electric circuit, the EMF across the parallel branches will be the same. The voltage acting across the parallel branches is the same. Similarly, in a parallel magnetic circuit, MMF across the parallel branches will be the same. So same MMF appears across these two branches, or we can say that the total MMF across this circuit, the total MMF of this circuit is equal to MMF required for this reluctance plus MMF required for the parallel branch. And MMF required for the parallel branch is the same. MMF required for path BAFE is equal to MMF required for path BCDE. So we can write total MMF of this parallel magnetic circuit is equal to MMF of this path plus MMF of either one of this path, because both of them are same. So total MMF is MMF of this path plus MMF of this path or this path. That is, total MMF is equal to MMF required for the central limb. This one denotes the central limb. MMF required for the limb BE. MMF required for the path BE plus MMF required for either one of these paths. So MMF required for the path BE plus MMF required for path BAFE or MMF required for path BCDE. Okay, so we can write the total MMF is equal to MMF required for path BE. So we can write the MMF required for path BE or the central limb as S into phi. So S into phi plus MMF required for path BAFE, that is phi 1 into S1 or S1 into phi 1, or otherwise we can write the total MMF as MMF required for the central limb, that is S into phi plus MMF required for path BCDE, that is S2 phi 2. Okay. So this is the expression for total MMF of a parallel magnetic circuit. That is, total MMF is equal to MMF required for the limb on which the current carrying coil is wound plus the MMF required for any one of the parallel paths, parallel magnetic paths. Now, from the circuit, we can calculate the equivalent reluctance of this parallel magnetic circuit. So here S1 and S2 are in parallel, and this parallel combination is in series with this reluctance S. So we can write for this particular circuit, equivalent reluctance is equal to, the reluctance S is in series with the parallel combination of S1 and S2, that is S1 parallel to S2, which means S plus S1 into S2 divided by S1 plus S2. So this is the equivalent reluctance for this particular case. So for a parallel magnetic circuit, always keep in mind that for that particular limb over which the current carrying coil is wound, the total flux will be carried in that limb. So total flux is produced on that limb over which the current carrying coil is wound. So it may not be always on the central limb. The coil can be wound over the left limb also. In that case, the total flux will be present here and it will divide through this path and through this path. Okay. So consider the equations accordingly. So on the limb where the current carrying coil is wound, the total flux is produced. The flux then divides and carried by the other paths. And total MMF is equal to MMF required for the limb over which the coil is wound plus MMF of any one of the parallel paths.